Good morning to everyone. In today's video, we are going to see the superposition theorem with AC excitation. Already in our previous videos, we just come across with superposition theorem for DC excitation, as well as if the circuit is consisting of dependent sources. If the circuit is consisting of dependent sources, how to perform the superposition theorem. These two things are we seen already. Now in today's video we are going to see the superposition theorem with AC excitation. There is no much difference between your AC excitation and DC excitation. The only main point here, how we are using this cal-C to calculate your AC parameters. Okay, in this AC parameters you may observe this one. This is in polar format and these are in rectangular formats. We have to convert this from one format to other format to calculate your upcoming calculations. So the main important point here is how to use your calculator. Okay, that is only the main important point. The rest of the statement and the way of solving your problem, all the things are same as your DC excitation. Okay, so please go through this numerical. So in this numerical they ask you to find out your voltage across this 2 plus J5 branch. Okay, they ask you to calculate the voltage across the 2 plus J5 branch, and they continue the question, okay, by using the superposition theorem. If they didn't mention this statement using superposition theorem, you may calculate this one by using your mesh analysis or by some other theorems you can find out, but they say using superposition theorem, so you have to follow the superposition statement and the way of calculation. So what is the superposition theorem? If the circuit consists of more than one source, you have to consider one source at a time. And the summation of either voltage or current, you may call that one as a response. So whatever the response they ask you to calculate, it is the algebraic sum of the responses you get when you consider one source at a time. Okay, so if they are here, they ask you voltage across 2 plus J5. Now I am considering source 1 first, one time. I am considering source 1 one time, and I find out what is the voltage across this branch. In the second case, I consider this source and calculate what is the voltage across here. So the sum of these two responses, okay, the sum of these two responses is equal to the case where these two sources are applied at a time. Okay, applied at a time. That is your superposition theorem. So we just follow here. So here as a case 1 or step 1, we are considering the source 1, that is your voltage source. When you observe this circuit also, you can able to find out one source is your voltage source and another one is your current source, and here the elements are connected in T circuit. Okay, so now we are going to consider voltage source alone. So when you consider this voltage source alone, the current source is supposed to make it reduce to 0. So when you reduce this voltage source to current source to 0, this current source acts like an open circuit. When it is acting as an open circuit, no current is flowing through this terminal or to this branch. Okay, so no current is flowing here. So when no current is flowing in this branch, okay, so if anybody have any doubt, so I'm just drawn. So this current source is open right now. Okay, acts like an open circuit. When it is an open circuit, no current is flowing here. That means whatever the current from your source, it is tends to flow through this branch. Okay, through this branch only. Okay, no current is flowing here. Then what about this capacitor? What is the current flow in this capacitor? No current, zero current is flowing here. When zero current is flowing through this capacitor, what is the use of placing here? What is the use of placing this capacitor here? So that such type of elements we call it as an reductant elements. We call it as an reductant elements. Instead of drawing like this, if you remove this entire branch also, there is no issue. There is no issue. So the rest of the circuit consists of voltage source in series with an J4 ohms reactor and 2 plus J5 branch. Okay, that is your circuit. So when you observe this one, this is looking like a series circuit. For a series circuit, whatever the current flown through this branch is nothing but the total current flowing through your circuit in the series circuit. Okay, so to find out the current flown through 2 plus J5 or entire circuit is same. Entire circuit is same. So to find out the current in this loop, to find out the current in this loop, how we are going to perform? We know I equals to V by Z. So what is the V? 50 angle 0. What about Z? These two are in series. Okay, these three are in series. J4 plus 2 plus J5. So it will be 2 plus J9. So from here onwards, the main usage of your calci should be known to you. Okay. So in the numerator, the voltage is in 50 angle 0, and the denominator, the impedance is in rectangular format 2 plus J9. Here I am going to show the two methods. Either you can directly calculate from here, that means in the numerator if you have the polar, and the denominator if you have the whatever called rectangular element, how to calculate. The second the another method is you have to convert this rectangular into polar. From this polar we calculate the answer. Both the methods we will see. Okay, so first method, I just want to convert this rectangular into polar. From the polar I calculate what is the final answer. So for any case you have to keep this setup, I mean mode, in complex. So I think the calci is visible to you. Okay, so the mode is in complex. Okay, so now I just want to convert this denominator 2 plus J9 into polar. So 2 plus, even it is J9, we should write into 9I. Okay, shift engineering. So now I want to convert this one into polar. Okay, now I want to convert this one into polar. This is rectangular. So for to convert into polar, again click on a shift and 2. So here I just you may observe this, it is in complex. Shift 2. Now it is asking you whether you want the argument or conjugate, or you want the polar, or you want the rectangular format. What I required? I required the polar format. So click on 3. So the value what you entered, it will be converted into the rectangular and gives the answer. Here it is in somewhat square roots, all the things. I just want to convert into decimal by clicking here. Okay, so S to D, when you convert this, it will be converted into decimals. So 9.219. So the third element is greater than 5. I just added 1 to round off it. So 922 angle of 77.47 angle. Okay, so this is the denominator. So when you have this, I just converted the rectangular into polar. So if I want to divide the two polars, okay, please remember this point for whatever the case. Whether you want to perform the addition or subtraction, go for the rectangular formats. So addition and subtraction is very easy to perform through the rectangular formats, A plus JB format. If you want to perform the multiplication or division, you may choose the polar. Why multiplication and division is for polar, and why addition and subtraction is for the rectangular? So if I have any addition like this, I can simply add the real values for real imaginary values to imaginary. Similarly, for subtraction also I can do this. So it is easy to understand why we go for the rectangular. When I go for the polar, the the multiplication and division can be performed. So if I want to multiply, okay, so I just take this alpha 1 beta 1 into alpha 2 angle beta 2. It can be written as in such a way that alpha 1 into alpha 2 angle of beta 1 plus beta 2. That means if you want to perform multiplication of two polars, the magnitudes can be multiplied but the phase angle should be added up. Similarly, if I want to perform this division, for division how should I perform? Magnitudes will be divided, the phase angles will be subtracted. Okay, so please remember these two formulas. Even this one is you studied in your complex numbers in your plus 2. If you may forget right now, so please remember this one. Okay, so now 50 divided by, so this is a normal arithmetic calculation, no need of making it as a polar or something else. So sorry, I just use, so I just want to divide. So 50 divided by 9.22, so I just 5.42. So when it is in denominator, when it becomes taken to the numerator, it will be minus. The phase angle should be subtracted. So angle of minus 77.47. It is understandable. Okay, this is method 1. So converting this rectangular into polar, from this polar we have to divide. The another mode method is there. From there you can simply directly given whatever the, whether it value is in polar or rectangular, whatever maybe, you can directly calculate. So how to calculate? The first step is same thing. You have to keep your mode in complex. Okay, that is the first step. The second step is you have to give the instructions in such a way that the coming output also, whether it is in a rectangular or polar, after doing any arithmetic calculation, the result also will be in one format. You have to provide. How to provide the solution format? By clicking the shift mode, shift plus mode. After clicking shift and mode, you can able to observe various forms of results. So please bring it down. So choose the complex. Okay, choose the complex by clicking 3. Here it is asking complex result. Okay, complex result. They are asking the complex result. Mostly I am go with polar format. Okay, polar format. Now up to here we can calculate. Up to here we have to we can calculate. So now I just want to divide a polar and a rectangular. So I just giving the numerator as polar. So 50 angle 0. In the denominator 2 plus 9 I. Okay, so this is the division. Directly simply how the remaining values you giving, the same way you are just providing this also, and click on equals to. It's giving some square roots, all those things. I just want decimal. So 5.42 angle minus 77.47. The same thing we got. Okay, so this is only the some little bit tricky to understand. The rest of the things are same like your DC excitation. So I got the current here. So once I got the current, to find out the voltage, I know. So to find out the voltage, V is equal to Iz. So I is in polar. So for multiplication, which format we should go? We should go for the polar format. So please remember whatever this values here I mentioned previously, that is only for the division. Okay, that is only for the division. Multiplication it is not available, only for the division. So now I should convert this 2 plus 5j into polar form. So I just considering, you can, so 5.38 angle of 68.19. so multiply these two, 5.42 into 5.38. so if I calculate 29.16 angle, so angle you can simply calculate it, it is in arithmetic, minus 77.47 plus 68.19, it is minus 9.28. so because of your 50 angle 0, because of your voltage source 50 angle 0, this much of voltage is available across your 2 plus J5 branch. Okay, this is case number 1. Now go for your given circuit. So now with this source we completed. Now we have to switch for this source. This is the current source. What about your voltage source when it is reduced to 0? It acts as short circuit. So the redrawn circuit will be looking like this. Okay, so when I consider this current source alone, this is the case. So when this case, now whatever the current here it is coming 20 angle 30, it is up to this node, it will be there. So when you are having two parallel branches, obviously the current goes to divide. So by you applying your current division principle, you are supposed to calculate what is the current flowing through your J5 ohms. Okay, 2 plus J5 ohms. So for this, total current multiplied by opposite branch impedance divided by total impedance. So 20 angle 30 into J4. We already know J operator is nothing but 1 angle 90 degrees. So 4 angle 90 degrees divided by 2 plus J9. Already we calculated previously. 2 plus J9, 9.22 angle of 77.47. So again it is in simple arithmetic. 80 divided by 9.22 angle 120 minus 77.47. so simply we can calculate. There is no that much of arithmetics to calculate. So again I have this current. So when I have the current, if I multiply it with impedance, I can able to find out what will be the voltage. So now I have the voltage because of the source 1 and the voltage because of the source 2. The arithmetic sum of these two sources will gives you a total voltage source. I already stated one point. If you want to add, you have to go for the rectangular, or add or subtract, you have to go for the rectangular. Addition or multiplication or division, go for the polar. So now whatever your results are there, it is in polar format. Now convert this one into rectangular format and calculate your answer. So already previously I just shown how to convert from rectangular to polar. Now we check for the polar to rectangular. So the same way, there is no that much of complicated. 29.16 angle minus 9.28. okay, so we have to convert this one, shift to complex. It is asking you to for rectangular 4. okay, 28.78, because I just round up this, minus 4.70. okay, similarly do for this one and get the final answer is in rectangular. Anyhow, when it is in polar, it is very easy to understand. Okay, so this is the thing, how to calculate a superposition theorem for AC excitation. Especially the usage of calc is important for AC excitations. Okay, so please understand this. With this I just want to conclude. Thank you.